All right, so chapter 20 is all about inducing current in a loop of wire that has no battery of its own. Okay, so for example, so those of you sitting in the room here, I already said this, but let me do it again for purposes of the video. So if you have a loop of wire like this, and I asked you to find the current in there, you're going to be like, what? How do you find the current in there when there's no battery, right? So back when we did circuits, we learned that voltage, delta V equals IR. If you don't have any voltage, you're not going to have any current, right? Because if you rearrange this, current is delta V over R. If there's no voltage in the circuit, you're not going to have any current. But what we're going to learn in this chapter is that it's possible to generate current in a loop of wire that has no battery of its own. So how do we generate current in a loop of wire that has no battery? Well, to understand this, you first have to know what magnetic flux is. And magnetic flux by itself is not very interesting. Like on a test, very rarely are you going to be asked, like, okay, here's the loop, calculate the magnetic flux. Because magnetic flux by itself is like, it's not very interesting. It becomes interesting. Magnetic flux becomes interesting when it changes, when there's a change of magnetic flux. So for starters, what is magnetic flux? How do you calculate it? So magnetic flux has this funky symbol. What is this? The Greek letter phi. Who knows their Greek letters? Is that phi? I should know that. I'm the teacher. Phi? Let's go with phi. So it's like the circle with a capital I. The symbol for magnetic flux is that, and the way you calculate it, it's the product of three things. You take the magnetic field, which is B, measured in, what do we measure magnetic field in? Tesla. You take the area of the loop. So all these problems are going to involve some sort of loop. A is area, measured in meters squared. And the loop is either going to be a circle. How do you find the area of a circle? Pi r squared. Or it's going to be like a square. And in that case, you go length times length, right? Area would be length squared. Okay? That's how you do it. Now, theta is the tricky part of the equation. What theta is the angle between the B field, the magnetic field, and the normal line to the loop. So what I have over here, in fact, let me erase this. This is kind of confusing, I think. Erase that guy. So what they're showing here in this diagram, so we have this magnetic field. We got this magnetic field that's coming in at an angle. In the flux equation, this theta, it's the angle between the normal line to the loop and the field. What does normal mean? Perpendicular. So see this dotted line right here? Dot, 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 dot. That represents the normal line to the loop. So if the magnetic field is coming in like this, the theta is going to be that. Does that make sense? So you got to visualize the normal line to a loop. And what I like to do, so look, here's a loop. I'm holding a loop up. What you can do is like grab a pen or a pencil and just stick it like that, okay? So that pen, this white pen, is sticking out perpendicular to the loop. Now, what if the magnetic field is going straight into the loop like this? What would the angle be between the normal line and the magnetic field? Zero. In that situation, the angle between the magnetic field and the normal line is 0. What is cosine of 0? 1. Cosine of 0 is 1, which gives us maximum flux. Now, why would this be maximum flux? Because the magnetic field can get into the loop with no problem, right? It just goes bam, straight into the loop. Now what's the other extreme? The other extreme would be the magnetic field coming at the loop like this, okay? Where it's like, you know, where the magnetic field is like parallel to the plane. If the magnetic field comes in like this, now what's the angle between the normal line and the loop? 90. And what's cosine of 90? 0. Let me write that down. Cosine of 90 is 0, and this would be 0 flux because why? Why does it make sense that this would be 0 flux? Because the magnetic field cannot get into the loop, right? It's going like this. It cannot enter the loop if it crosses it like that. Does that make sense? So we have maximum flux when the theta is 0, and we have 0 flux when the theta is 90, okay? So that's all flux is. Flux is the product of those three things, B, A, and cosine theta. Now, this becomes interesting. This becomes interesting whenever flux changes. Whenever the magnetic flux in a loop changes, we're going to get what's called induced voltage. And you guys all know the word induced. Induced means to make something there that was not there a moment ago. Like they use it a lot in the medical field. You could induce what? A coma. If you're in a bad accident, the doctor will induce a coma. If you're a big, giant, pregnant lady and the baby's not coming, they will induce labor. They'll put that mom into labor, right? I've seen it. It's pretty crazy. One moment, my wife was not in labor. The next moment, she was. They induced labor with, what's that drug? Pitocin is the drug they use. Okay, so here we're going to be inducing voltage. So you have a loop. You got this loop of wire. There's no voltage in it. One moment, then the next moment there is, because we created a change of flux. Okay, so how do you calculate induced voltage? So first off, this chapter is using this symbol for voltage. So you might remember this from circuitry. This cursive symbol E comes from EMF. EMF is it's another name for voltage. EMF stands for electromotive force. It's the same as delta V, which is voltage. Okay, so all these terms mean the same thing. You're going to be seeing this symbol a lot. Cursive E, EMF. EMF is the same as voltage. Okay? So how do we calculate the induced voltage? So the induced voltage is this equation. You take N, which is the number of loops, which most often is just going to be 1. You know, like this loop right here. How many coils or how many loops is this? 1. It's 1 loop. But if I have this, so this thing is copper wire, and whoever made this went loop, 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 probably like 100 loops in here. Okay, so N is the number of loops in your coil. All right, and then this is the change in flux. Now look here. There are 3 ways to change the flux. What are the 3 ways to change flux? Well, look at the flux equation. Over here we got the flux equation. What are the 3 ways that you could change the flux? You could change the field, right? The strength of the magnetic field. You could change the area of the loop. Or lastly, you could change the theta. Okay? So let's look at 2 situations. I got 2 diagrams here. So what we have right here, this comes from an AP question. So look at this diagram right here. So we got this cart that rolls in to a region of magnetic field. So in fact, let me try to back this cart out. Let me see if I can grab him. Here we go. So the cart is not in the magnetic field yet, okay? How much flux is in this loop before the cart enters the region of magnetic field? 0. The magnetic flux in that cart is 0, right? So then what happens? The cart rolls into the magnetic field. What's changing here? Are we changing the field? Are we changing the area? Or are we changing the theta? Which one would that be? It's the area, right? We're changing the area that's exposed to the field, right? As the cart rolls into the magnetic field, more and more and more of it is exposed to the magnetic field. Do you guys follow that? Okay, let's look at this situation over here. Okay, so what we have here, here's a magnet. So the magnetic field is going from the north end of the magnet to the south end of the magnet. So there's, in this space in between, the magnetic field is shooting that way, from the north end to the south end. And what they're doing is they're taking this loop right there and they're rotating it. The loop is turning in there. So what's happening in this situation? Is the B changing? Is the A changing? Or is the theta changing? The theta. If you take a loop and you rotate it through a magnetic field, you're changing the theta, right? So those are just 2 examples. Now, lastly, time. How does time affect the induced current? How does time affect it? Well, the quicker you change your flux, the what? The bigger the induced voltage or the smaller? The bigger. Now I'm going to give you guys a demo in a moment that'll kind of make this a little more clear. But look, it's not too bad. The thing to remember is, you got to know how to calculate magnetic flux. Whenever that magnetic flux changes, there's going to be an induced voltage. Oh, and I should add this. What does induced voltage lead to? Induced voltage will lead to what? Induced what? Current. Induced voltage causes induced current. How do you calculate the induced current? Once you have the induced voltage, how do you find the induced current? With delta V equals IR. Or for this chapter, you're going to say E equals IR, because delta V is the same as E. Those are identical. And then you can solve for the induced current.